Right, so as promised, a hard example. So, I'll let you read the question. Now, because the rope is 16 meters long and the climber starts off 8 meters below the point where the rope is attached, the climber can fall 8 meters. So, at the point when the rope becomes taut or some tension begins to build in the rope, the climber will have fallen 8 meters, and so we can use CVAT equations to work out the speed of the climber when the rope becomes taut. So that's what we do for part A, and that's nice and easy. In part B, the maximum distance of the climber below the ledge is, well, here we have the ledge, it's fallen 8 meters. Here is the natural length, so this is 8 meters. Here's the equilibrium position caused by tension, and the fact that the tension will be equal to 70 G, and then he will oscillate, okay? Well, the climber will oscillate, and so it's the lowest point of this oscillation, which of course we call the amplitude. So, it's looking like a wave, because we're talking about an oscillation. So, you could use conservation of energy here, because the maximum distance of the climber below the ledge is the point where the climber has 0 kinetic energy. And so, we have the option of doing it with conservation of energy or SHM. I'm going to choose SHM just because it's an SHM module. Okay, so tension, easy to calculate, is equal to 70 G, and we can rearrange that to find E. Okay, and then, because E is the point of equilibrium, we can find the amplitude. So finding the amplitude isn't that hard. Okay, we've got this in terms of E. So, for the oscillation, we have the sum of the forces is mass times acceleration, so we have 70 G down, and tension acting against weight. And so we can say that the extension is X plus E. Okay, I've got that E anyway. Now we've got a term for E up here, which is a good starting point. So, if we're just looking a little bit closer, here's our term for E, and when we expand that, there's a few things that cancel. So I'm cancelling a common factor of 10, just to shorten the equation a little bit. And then when I expand this further, because of my term in E, I get a 7G that will cancel, and I'm left with a very simple equation that shows that this is obeying SHM, and we've got this as our omega. Now to go from omega to the displacement is relatively easy. Okay, I say relatively easy because we have a velocity, and this is the velocity at the start of the oscillations. Okay, so next page. Our omega was 250 over 7. Our velocity, I said, was the starting velocity, and we can simply put that in to the equation. We have a value for x, and then that gives us an a squared, which we can find. Okay, it's the only unknown, and rearrange, and we get a value for a. Now that value for a can be added to the 8 meters that they fell before the rope got taut, and the displacement, not the displacement, the extension. So we've got maximum displacement, extension, and the total distance that they fell, and that gives us 10.38 meters. So that's the lowest point that they will be below the ledge. And this is where the question gets a bit difficult then. So I asked Pablo Picasso for a little bit of a helping hand just to try and illustrate what was going to be happening, and he said no, he couldn't help, and so I had to do some drawings myself. So here's a man on the ledge, here's the ledge, here's the man falling, here's the man still falling, and he becomes an oscillator. Okay, here's the extension. Okay, this gives us a point of equilibrium, and he's now a wave. So the amplitude of the wave is here. However, because this isn't a spring, okay, he's only under tension from the point where obviously the rope goes taut, so at 8 meters below the ledge. Now, as the amplitude is bigger than 8 meters, we have a false area. So what we're going to do to calculate the time between falling and the lowest point, we're going to work out the time it takes to fall. Okay, then we're going to work out the time, or the time that he's in free fall. We're then going to work out the time for a complete wave cycle and divide it by 2. It's half a wave cycle because he just goes down, he doesn't go down and then back up. And then we're going to subtract this little false bit that I've labelled n, this no bit that doesn't actually happen, where he's still in free fall. And he's in free fall, and so the wave isn't applicable. Now we can still use our wave equation, because our wave equation doesn't know it's applicable. It thinks that he's under SHM for the entire amplitude. He's not, it's just from E. So what we need to do is we need to take the amplitude, take away E, and that gives us N, this false point that we can take away. So it gives us this false time. So we've got the time under gravity and the time in oscillation. Take away this false time is our total time. Now, if we start off with a cos wave, okay, so we're at maximum displacement initially, then we can just have the oscillation go from maximum displacement to E, okay, and then we can work out the time. So that's exactly what I'm going to do here. So let's just zoom out. We have starting at maximum displacement, so we use cos. Here's our amplitude, and we're going to let x equal to E, so as we can find this false time, the time it takes to get to this point where all of a sudden the string goes taut. And so we have x is 7g over 250 is equal to this. Okay, so 7g over 250 divided by 2.13, then inverted cos to find root 250 over 7t, and then get rid of the 250 over 7 square rooted. So that gives us our time. So the time that the rope is taut is the period. The period is 2 pi over omega, so 2 pi over the root of 250 over 7, so that's 2 pi times by the root 7 over 250. Halve it, and obviously it's been halved because it's only 1/2 of the oscillation from down, so from up to down. Take away this false time that we found above, and this is the time that the rope is under tension. So the time that little Mr. Climbing Dude spends falling, very easy to find from Suvat. Okay, falls 8 meters, under gravity, he's initially stationary. And so we get t squared is 16 over 9.8, so the total time is root 16 over root 9.8. So 4 over root of 9.8, plus the time in oscillation, that gives us a total time of 1.56 seconds. So that's easy enough mathematically. The difficult bit is this conception. Obviously, if he were attached to a spring, then he's going to be under compression. The spring's going to be under compression here, and so the oscillation is still valid. But because it's a string and not a spring, there's no tension under compression, and so you just have to get rid of this. Okay, so look over that again. Hopefully you'll understand the steps that I've taken, and you'll be able to try some of the questions with relative ease. Good luck.